Well, thank you very much. So clearly after 6 months of fabulous Tuesday seminars, here's the anticlimax. So I would like to talk about model structures on finite lattices. And why would I like to do that? Well, model structures generally, they come to life if you would like to talk about certain categories relevant somewhere else that you would like to understand, be that some homotopical algebra or standard topological spaces, rational homotopy theory, highly structured ring spectra, or whatever. And you need to really understand those categories and what to do with them. Whereas if we are now looking at some rather petite categories, things that are becoming very, very hands-on, and we can actually see, really focus on the model category stuff rather than what you are going to apply it to. So on the one hand, this gives us a nice almost gateway drug into the maybe more complicated types of categories and formal constructions there. But also more surprisingly, at least when I first saw it, these constructions, or really these teeny tiny categories, are very much related to constructions in equivariant homotopy theory, as we have seen in the previous conference and very much in the Belfast conference. So, lattice, finite lattice is a pole set where objects have unique meets and joins, so supremum and infimum type objects, and really you can either think of your finite one, favorite one. Do you all have a favorite finite lattice? I know if I do, to be honest, but so the ones I would like to think of is either some finite total order like this, where you have arrows from the smaller one number to the bigger one, or if we're getting really daring, we have something like this today. Or really daring one with like 2 cross 1. And I'd like to point out, because that is something that you can really stumble over whenever I write anything like this. Arrows go from bottom left to top right in sort of coordinate notation rather than matrix notation, because it took us a few papers to get settled on the direction, and it's particularly fun when you do lifting diagrams and you have no idea which way your things are going. But anyway, normally, whenever, probably since 2004 or something, when I first met Marcos, yeah, you were there at my very first conference talk. Yeah, I was in BM in Heidelberg. Yeah. How is that possible, given that we're only 25 years old? So normally, whenever I start motivating a talk about model structures, I would say, well, we can do homotopy theory and things like topological spaces and so on. But today we are going to do model structures on these things, but I would like to write down the definitions anyway, just so that we have notation and I can point out the things that will be particularly important to me. So, we know, or may not know, or tend to know, that a model structure on an underlying category is something where we call morphisms weak equivalences or co-fibrations or fibrations. Well, some morphisms are called either weak equivalences or co-fibrations or fibrations, or none at all, or combination of those. And these 3 labels have to interact with each other via some axioms. And if we have both weak equivalence and co-fibration, we call it an acyclic co-fibration. And likewise, if we have both weak equivalence and vibration, we call it an acyclic vibration, and now the axioms are quite easily summarized as follows. So a retract of one of those things is again one of those things. The weak equivalence that satisfy the 2 out of 3 property. So if you have an F, a G, and a G after F, if 2 out of 3 of those are weak equivalences, then so is the third. Lifting is always fun. So if you have a commutative square, where on the left you have an AC and on the right you have an F, then you can always have a little lift. Yeah, you can. And you can also write possibly slightly dual version if you have. What did I do?
I meant.
Yeah, I know. I will point that out very, very carefully when we get to it, but I really set myself up. So in the regular notation, if you have a commutative square, you have a lift, and you can factor your morphisms either as whole vibrations followed by acyclic vibrations, or acyclical vibrations followed by vibration. So far, so good, but rightfully you might ask yourself, if we are just looking at these things like I asked you to, and if you're always thinking of your favorite finite lattice or whatever, do these things become simpler? Well, first of all, I mean, there are no retracts in pole sets because you can't get bigger and bigger and end up where you started with. So, so that actually goes straight into the bin. But also, the weak equivalences do not just satisfy 2 out of 3, but they are decomposable. So if you have a composite that's a weak equivalence, then you know that each of these has to be weak equivalent as well. And we showed you a proof yesterday, Clark. It is actually quite a cute little proof, so I might as well do it. So if we call this one F, then we can factor our F. Yeah, that's F. We can factor the F as yeah, I know those doesn't really matter because of 2 out of 3. It will be both anyway. So and then I want to factor my G. I want to factor my G as well, and the G I would like to put the weak equivalence onto. And yeah, because we're in a pole set, well, we have a lip because we have, and because we are in a pole set, this one is actually a push out of this one. Because a push out in a pole set is just moving. The right one, the one. So that would be a push out, meaning that this would be an acyclical vibration as well. And then because of 2 out of 3, I know that this one has to be weak equivalence. Yeah. So I always thought it was horrible because it has been quite a difficult technical paper, but so far not so bad. But something that we always know homotopy whole set, we know that there is a lot of redundancy in that definition because most of the time, 2 out of those 5 things, unless you pick the 2 wrong ones, determine all the other ones. So it is enough to know your entire model structure. You only really need to know the weak equivalences and the acyclic fibrations, for example. Because if you know these 2 things, because of lifting, if you know the acyclic fibrations, you know the co-fibrations. If you also know the weak equivalences, then, well, you know the intersection with weak equivalences. And once you know the acyclic co-fibrations, vibrations. So if you just know those 2, you know everything. But then, of course, why would I have picked this particular presentation of this? Well, also in general, acyclic fibrations and fibrations, of course, but also acyclic fibrations are closed on the pullbacks. So far, so not new, but now going back to language used elsewhere in this program, if you have a wide subcategory closed under pullbacks, this is what some people call a transfer system. And transfer systems, well, the categorical definition really is just a wide subcategory closed under pullbacks. But I first saw transfer systems on one of the boards next door in 2018, when, well, if your underlying pole set is subgroup lattice of finite abelian group G, then a transfer system is equivalent to the following data. So you have pairs of subgroups of G such that if you have 2 composable pairs in your transfer system, that's T, then so is the pair from the smallest to the biggest. And restriction was that if you have a pair in your transfer system and just any other subgroup, then you can intersect this pair, so restrict it along N and get another pair of, well, get another pair in your transfer system as well. And that goes back to those dots up there, in the sense that this would be the subgroup lattice of cyclic group of order P to the N, and well, that would be cyclic group of order PQ for distinct primes P and Q. And it's kind of nice and also, I think, informative for some examples to remind yourself of these 2 equivalent definitions when you're actually trying to write something down or draw something, because then, of course, you can then go and represent these things by a graph with arrows in your transfer system satisfying certain rules. So, what what do we therefore have for a model structure? We have on a finite lattice something that is closed under the order 3 and decomposition, and we have a transfer system that lives on, so is supported, and that is really the data of a model structure that leads. Yeah, that is the data of a model structure on a finite lattice, rewritten in some other language. So, if we therefore go on that first lattice up there, you see that.
You can raise it up when I want.
So on here, page work with Scott Martin, Hal Ormsby, Angelica. That's on a total order. This is exactly what also determines the model structure the other way around. Yeah, it's a great day. What can you do? So really, if you have a model structure, it really is the same as a partition on there and any transfer system that lives on that partition. Because of the decomposability of weak equivalences, you really only need to know if a map from I to I plus 1 is a weak equivalent, and that gives you the partition data. And then, so we show that if you take any partition, plot a transfer system on it, you get a model structure. And of course, we already know that if you have a model structure, it gives you a partition or a transfer system. So,
Constanze, maybe
yeah.
you said this, but so far I've gotten that if you have a model structure, you have W comma AF.
Mm-hmm.
Does it go backwards? If you have W comma AF, does that automatically give you an auto? So that would just define the.
Spoilers.
You can answer this question. Okay.
Very soon, in fact. But we always want to start somewhere where the world still looks all right.
Just see.
So, in this case, it means because of work that other people have dedicated their lives to in combinatorics, there are various formulas involving partitions and capitals and all sorts of things. So one can actually there is a closed formula, which for some reason I didn't put down in my notes, just depending on n, how many model structures there are on the n total order, because you can count the partitions, and then for each partition block you can count the options of what transfer system you can put on it, and that is that number that you get. But if we just say, just take it a little easier, I mean, we've seen a lot of dots and arrows today, and now it's just 3. So, let's say, what model structures can we have just on this little category? So, there's not that many ways to partition it. I can either do this, or do this, and this. Or I could just have absolutely everything is a weak equivalence. So that is my options for weak equivalences. And then one can say, okay, so how many how many transfer systems can we put on each block? Well, in this case, there's only one option. And here you have two options, because either you add this map to your transfer system or you don't. Same here. And in this case, there are 5 options for your choices of acyclic vibrations. That, or that, or that, or this, and everything. So that means that on 2 you have model structures. Nice. So if we're now getting on to the next case, we will see what Paul has already been suspecting. So once it also means once you know your transfer system, you can just cook up a recipe to make all the model structures you want. So on this little square, there are these 3 models. I mean, you can just leave that, but or it's, you know, if there's a blackout and you have no TV, internet, or whatever, it will take a couple of hours. So how does one normally get to that without knowing stuff? So transfer systems, I can tell you, I think you can handle that. So transfer systems always arise at the right step of the weak factorization system. If you've never heard of a weak factorization system, and I haven't before I did that, immediately. A weak factorization system is basically half a model structure. So to get a whole model structure, you need a pair of weak factorization systems. And as the transfer systems are all the options of what you can put on the right-hand side of your weak factorization system, and then you can calculate what your left-hand side would be. So these are all the maps that live to the left of all of those maps. So you can work out what all of those are, then what all of those are, pair them up. To get your candidates to go on to you get things that may be part of a model structure, and if your W that you define as so satisfy 2 out of 3, then all the views come true when you have a model structure. And if you play this through with the 10 transfer systems you can put on the square, then you're left with 23 model structures. But who cares? Well, if you stare at them for long enough, one sees that while all the different W shapes that satisfy 2 out of 3 and decomposition on the square do actually arise as existing W's, not all of the transfer systems that live on it do. So all such W's, all these W's that you could think of actually are on the list that one I've generated rather brainlessly. But not all candidates for transfer. So look at one curious case. So here's my square. Let's say that these are my connected components, and my arrows, as I said, go this way. Well, firstly, we can observe that every short arrow, so an arrow that we can't decompose any further, but every arrow has to satisfy factorization. And that means that if my short arrow wasn't already weak equivalence, it has to be both vibration and co-vibration, because otherwise I wouldn't be able to factor it both ways. Which means that, but it also means a short arrow that is a weak equivalence has to be a vibration or a co-vibration for this to hold, and it can't be both, because it wouldn't really lift against itself. So this has to be either one or the other. But as John already pointed out very rightly, there is no lift in this diagram, because lift would have to go that way now, because we just draw them this way around. Because there is no lift, this thing can't be a co-vibration because I have a vibration here. So it has to be one of the two things. So it has to be a vibration. So on this constellation of W's, you have restrictions on what transfer systems you can put on there, and that is one where, for example, you can't put the trivial one. Because if you put in something that's not an acyclic vibration here, you'd be in trouble and violate your axis. So then, while that is of course like a nice let's just make it even worse. So let's go to the pole set we lovingly call the Berger pole set, which is, well, if we draw it, it doesn't look big Berger just yet, but as performing this procedure on this pole set with, I think 63 transfer systems, something like that, it would take a lot longer. So Scott's marvelous algorithm can just print all the model structures that arise on this pole set, and when you ask your computer to generate a PDF, you make some choices how you would like it displayed, and so the co-vibrations and the vibrations were just displayed with little arrowheads and hooks on the tail, and the weak equivalences were like orange, beigey orange. So I spent many afternoons looking at diagrams that looked a bit like this. So yeah, that's why it's now the Berger pole set. And on this one, not even this is true anymore. There are candidates for weak equivalence satisfying 2 out of 3 in decomposability. Which do not occur on the list. And on Berger, actually, the ones that cause you trouble are precisely those where this one is a weak equivalence sandwiched between two non-weak equivalences. Just this very morning, we managed to generalize that. So the question on whether or not a W is legal is quite non-trivial. And now I also have a task for you, and I'm sure John will be fantastic at that, because he was last time I had a problem with naming things. We've been calling those W's that do actually occur the legal W's, but the American people on this paper are not happy with the political loadedness of legal. So if you know anything else, that's not just admissible or something overused, then please let me know. So, so it is non-trivial to figure out which W's are legal, but it is now in very, very early stages that we think we can actually, we have necessary sufficient conditions to tell you. And if I'm sitting there tomorrow being very, very sad, that then you know that maybe the proof didn't survive the night, but we are optimistic. So there's really two separate questions there then. Which are the legal weak equivalences? And if you have a legal weak equivalence shape, which you know for whatever reason is legal, which model structures can you have on it? And well, this is pretty much this. Das kallas laser, Rika Savalam, Danica Camille, and Valentina Zapata. So in fact, so if we say we have a legal weak equivalence set, we can actually say what all the possible transfer systems are that we're allowed to put there. So we're all on the finite lattice. Then with the transfer system, T min volume are equivalent. Either you have a model structure. To have a model structure, you have to sit between T min and then it can get as big as. So if everything in T min is in, then you're good. And in this case, the little 2 by 2 square, the T min already had to include the only non-trivial choice. And that is not just a theoretical T min, we can actually say what it is, given the shape. So you, the acyclic cofibrations would form something called the co-transfer system, which is the same, just with push-outs. You take the biggest co-transfer system you could squeeze into your W, go through those motions that I've just erased. So these are your candidate acyclic cofibrations, and then you lift to the right, you get candidate vibrations, you intersect with W again, you get a transfer system, and that is T min. So if there is a shape where you know that that's a legal W, yeah, with a bit of elbow grease, you can figure out what the T min is. And if your diagram is not particularly big, it's not much elbow grease.
Are the conditions on W to determine when a W is going to be illegal?
Ooh. Is it a free theorem? What is it?
It's a 99% theorem. That's my level of confidence right now.
You said earlier 99.99.
Mark.
Okay. So as of today, W is legal if and only if the following two things hold. Every short arrow for its sigma in W, either all its pullbacks or all its push-outs are also weak equivalences. So this is why that's trouble, because that one is neither.
When you say either, do you mean exclusive either? So that only one happens?
No.
So it's one or.
Yeah.
Yeah.
Yeah, it can be everything's fine, but yeah, not nice. And then there is something on which not even any nodes exist. If I have something, if that is in W, and these are short arrows, if, well, let me just paraphrase it, if I take something and in W and I factor it into short arrows, because you can always factor into short arrows, then right at the end, you have things where all the push-outs, no, all the pullbacks are in W, and then at some point it changes to all push-outs. And we haven't really found a catchy formulation of it yet. But it isn't just that each of them has to either have all pullbacks or all push-outs, but if you have some map in W, then it has to start with basically all ACs and then change over to all AFs.
So these are this condition, this first condition is like characterizing the short
Yeah.
basic co-vibrations or the short basic.
Yeah, I mean, it's clear to see why this is necessary.
Yeah, and you're saying it's
Yeah.
also sufficient.
But that plus that is sufficient. So not only does every short arrow either have to have all its push-outs or all its pullbacks, they also have to fit together in a certain way.
Mhm.
Yeah. But I'm sure when we write it down again and again and again, we will come up with a easier logical statement, but you ask for it, so don't complain.
So in the example that we still have on the board, the last one, is there a W where the middle one is in W, but also the one on the right?
Yeah, so all the others that satisfy 2 out of 3 and decomposability, they will be on the list of 184 burgers, except for, well, you can also have like, you could have, I think this, these are the only 4 that do not. And these are precisely all the ones where if you just look at the vertical ones, that there are ones that have a sandwich between two more really products. But yeah, the ones where these 2 lines are come up, these 2 lines and other stuff as well. So yeah, everything else is legal apart from that. But then, of course, if you are in this situation, then you never have to worry about the second point because you don't really get longer strings or 4 hours. So yeah, that's nice. So, yeah. Of course, when one has model category structures, and now we know what all model category structures on our favorite lattice, finite lattices look like, maybe we'd like to do things. So what I like to do with model structures is I'd like to Bounce-Tree localize them. And yeah, because of Clark, everybody thinks that right localization is terrible.
You're right.
Well, we can do both. We can do both. So, let me so
May I ask a question?
Hmm?
So is there a way to say, like, do you know anything interesting about the map from the, because I guess if you invert the weak equivalences,
yeah,
you don't generate any homotopy theory because of this decomposability. So I guess the quotient is the homotopy category is another post.
categories are not that frilly.
Yeah, there's just another post set. So this is a map
Yeah.
of post sets.
Mhm.
And do you have a characterization, like, is there something to say?
Well.
about that? Oh, okay. All right, good. I'm just gonna sit here and be quiet.
No. I mean, that way it gives everyone the illusion that the audience is awake. So, I love that. So normally when you do left localization, and yeah, going back to the beginning, either people normally mention rational homotopy theory or just having a framework to formally invert things, which is always a challenge. And yeah, now, well, how does that work in the context of what we've seen so far? So both left and right localization, you would like to increase the weak equivalence. And classically, the definition says for left localization, you keep your core vibrations, and for right localization, you keep your vibrations the same. And, well, yeah, there are existing theorems, but we don't really have to worry about it on a finite lattice. So that also means that in this case, if this one becomes bigger and this one stays the same, it means that you get fewer core vibrations. Or in this case, because really, if we go back to our presentation of model structures as pair or as a legal W and a transfer system, well, if you left localize, now left localization is really, really, really boring because keeping the co-vibrations also means you just keep that. So you get something bigger here, whatever that is, and that just stays the same. Because if you keep the core vibrations the same, you keep the acyclic vibrations the same. So you know there's a book.
Yes.
40% discount. of a really nice free. But now if you right localize, you make this thing bigger, and you make this thing bigger. So that contains, yeah. So you make this one bigger somehow, and you also make this one bigger. Okay. So if you look at the transfer system aspect of browser localization, left localization is not particularly difficult or interesting. But yeah, right localization takes a transfer system and makes you another transfer system, a bigger one. And well, I'd rather not introduce all the notation necessary to do that, but I will probably draw a couple of nice examples. So the difficult thing is that I have to match my co-author surnames to their first names. So that is most of my notes, actually. Yeah. And there it already starts. Ah, yeah. Andres Canet, Patricia Royal, Devin Hensley, Sophia Martinez, Cherry Ng, and Daniel Tolosa. I'm not really able to write down what it is, but a minimal set called the golden arrows, such that, well, if G is a short arrow, that is all you need to know, because if you want to localize a long arrow, you just do several localizations of a short one. So there's a minimal set, just depending on the weak equivalence shape, such that the right, well, the bigger transfer system you get via right localization is the smaller one with the golden arrows added. The smallest transfer system that then also contains those. And then all the examples that you can draw, you can say relatively easily what it is. So if you have a two-dimensional grid, that's anything that can be drawn.
You now just add D to the weak equivalences,
The weak equivalences.
or what was the role of G?
I am literally only talking about here. The weak equivalences, I'm hoping as of this morning, I will have a better description of how the weak equivalences change under localization. But the weak equivalences need to be treated separately, and that is a bit outside of all of this. So in the cases where you know how the weak equivalences change, one can very easily say what has to happen. So if I take if these are my weak equivalence connected components, and if I localize at any of the short G's that aren't weak equivalences yet, the resulting new weak equivalence set is going to be all of it. And the arrows I have to add is I go to the components that are being joined, I take the maximal points of all of those and connect them up like so, and then the golden arrows in this case. So for total orders, that is something we kind of did without knowing that that's what we did. So if you join two neighboring blocks in a total order, and you want to localize at that arrow, then what you really do is you have a transfer system on here, and you have a transfer system on here, and you add this edge and then everything else that this edge forces you. So this is basically generalization of what is already in the paper for total orders. And the thing that this then helped us to look at is not just, okay, here's something, you localize what you get, but also how in general, yeah, what localization does to all of the model structures really, because on total orders, what you have is colors. On here, every model structure you can think of can be achieved as a sequence of left and right localizations from the drift. With the trivial one being that one in the top on the identity with equivalences. The proof of that was, well, you know what a model structure would look like, and you know what transfer systems look like. Can you mimic the process of building larger transfer systems out of smaller ones with adding arrows via localization? And the answer in this case is yes. So in general, this turns out to be false. So on the square, this works too. And Sophia has actually even just latex how the 23 model structures, how they're all coming from the trivial one. It's really nice. But on the burger, it's not that hard to find examples of something. Please don't ask me here and now, but on anything bigger than that, and therefore in general. And this is not true, but I don't just want to end all EHT seminars like that. So there is a notion of a saturated transfer. A saturated transfer system is, well, saturated transfer systems are particularly nice transfer systems which crop up quite naturally in multiplicative G spectra with norms and stuff and transfers. So for any transfer system on at least a two-dimensional grid, even though I think we can extend that to a more general modular lattice, it's true that every model structure where the acyclic vibrations are saturated can be achieved as left-right localizations of the trivial one. So I personally find it very intriguing that this thing which is relevant in equivariant techniques, like what are saturated transfer systems? Is it little disks?
Linear isometers.
Yeah. And multiplicative structures on G spectra as well, that these things also seem to be related to some very kind of, yeah, very finite abstract nonsense stuff like Gaussian localizations and these things. And I have found it very interesting just in the last couple of years to see how these things that are of quite different flavors just seem to pop up naturally in the same place via here. And yeah, that's hopefully maybe in 7 years' time, there'll be another program, and I'll come back and say, oh, in 2025 we did that, and look, we've now done a lot more, and that's what I would very much like to happen. So thank you for listening so far.
Questions?
So I guess it's surprising to me somehow that there are so many model structures on these really tiny categories. So like, I don't know, like the category of finite sets has
Yeah.
model structures, and then you take this like really tiny one that has only 2 arrows in it, and that suddenly has 10. Like,
Yeah, but also
what
if
is
you're tiny, there's not that many things that can go wrong. So
So the things that go wrong beat out the things that go right as the size of the category increases.
yeah, that's a very nice way of thinking of it.
Maybe I didn't quite understand what Clark asked before, but is there a way of classifying these up to them inducing the same, say, equivalent homotopy?
I've been meaning to look at what Quillen bundles look like, and therefore also what Quillen equivalences look like. And of course, just as a category, the homotopy categories are that interesting. But yeah, it's definitely something I would like to look at.
You can produce many different ones.
Yeah, I bet. Haven't tried. Wanted to. Was distracted by other things, but
But in brackets n is not very interesting because it's just about a number of parts in your partition.
yeah, but still, if you want to write down nicely what Quillen left and right Quillen bundles look like, one has to at least have a very long process.
If I understood rightly, so that every saturated transfer system in particular comes from a model structure.
Yeah.
Now, is there any interpretation in terms of subgroup lattice? I mean, in the case of when it's a transfer system on non-subgroup, is there any idea of what coming from a model structure would correspond to in group theory?
Well, John, this is very, very, very fresh. And last year I wrote a failed EPSAC application where I, among other things, asked exactly that. And I'd like to find out. And I think these are reasonable questions. I think it's good that somebody else also finds them reasonable. Yeah.
But as you're saying that if we're not just asking for there to be a model structure, but one that arises from
Yeah.
the trivial one by these specific operations, then you have to recover the saturated
Yeah.
structures on the right. So that's already a nice connection.
That's so very fresh.
Any other questions? All right, well, till 7 years now, time or so. Yeah.